Okay, so the next example we are going to do is we're going to do a integral over a closed curve. So the symbol here, this means it's over a closed curve. And our closed curve here is going to be the unit circle. Now, there's a lot of different parameterizations you can do for the unit circle. The standard one is you let x be cosine and y be sine, and we want to do a full rotation. That's something that you should, if you haven't already burned into the back of your skull, you should do so now. All right, so our x here is cosine, and our y here is sine. And again, that circle through the integral just means we end where we begin. Okay? But the process is the same. So what we're going to do to integrate over the circle is we're going to replace all the x's with cosines and all the y's with sines. But there are no y's. There is a dx though. So dx, if x is cosine, the derivative is negative sine. So that's the integral that we're going to compute. And this is so negative, pull that negative out, make it look a little bit nicer. Cosine sine dt. And whenever you see a cosine and a sine together, if the integral is not obvious at first glance, you usually try to do a substitution. Oops. I want u to be sine, so du is cosine dt. So then we have the integral from 0 to 2 pi, u du, which is the integral, negative of the integral from 0 to 2 pi. Oops, sorry, keep going too fast, gotta slow down. It's negative 1/2 u squared from t equals 0 to 2 pi. So that's negative 1/2 sine squared from t equals 0 to 2 pi. So it's negative 1/2 sine squared 2 pi. I'm going to do the subtraction this time. Minus 1/2 sine squared of 0. But both of these guys here are 0 because they're sine of a whole multiple of pi. So we get 0 for this integral over a closed curve. And in fact, if you remember Green's theorem from multivariable calculus, the integral over c of x dx should be somehow, it should be somehow related to the, so as just a quick reminder, the integral over, the closed integral over a curve of p dx plus q dy is related to the double integral over the region that the curve bounds of, I'm going to mess up the order probably, qx minus py dA. So here our p is x, and Green's theorem would tell us we have to integrate over the disk, because the circle of radius 1 bounds the disk, of qx, there is no q, so that's 0, and then p is our x term here. We have to differentiate that with respect to y, but we get 0. We're integrating 0, we're supposed to get 0. So, if you don't remember Green's theorem, that's fine, but if you do, we can use that to compute this integral, and it's a lot less work, as you can see.